Okay, if not, I'm sort of officially ending the lecture. This is, well, lecture done. Office hours, bring them in. Let's share screen with the homework. So, you know what? I'm just gonna go through the homework. If you have a question, let me know. Can everybody see the chapter 24 homework right now? Somebody give me a yes. Somebody, yes. Got a more chat. Yes, okay. So first one, and let's just kind of go through this. And you know what? I don't mind doing this because I don't know. Yeah, I'm still figuring out the best way of doing all this online, but I think this will prove useful. So first one was, all atoms have moving electric charges. Why then aren't all materials magnetic? And it's similar to, all objects have trillions and trillions and trillions of charged particles. Why aren't they all charged? It's because, like for charges, for every proton I have an electron, I have the same number of positive and negative charges. Well, in terms of magnetism, all moving charges create a magnetic field. Most magnetism comes from electron spin, but most materials have electrons whose magnetic fields cancel out. Just like the positive and negative charges cancel out, so most objects are neutral, most objects have magnetic fields that act in opposite directions that cancel each other out. It's generally only iron, nickel, and cobalt that have more atoms or more electrons with magnetic fields in one direction than another. So most materials are not magnetic because the magnetic fields of all the moving charges cancel each other out. 2, your study buddy claims an electron always experiences a force in an electric field, but not always in a magnetic field. Do you agree? Why or why not? So 1, an electron does always experience a force in an electric field. It doesn't matter if it's moving, doesn't matter if it's at rest. If there's an electric field and there's a charge nearby, that charge will experience a force from the electric field. Now, for a magnetic field, 1, the charge has to be moving. A stationary charge does not feel a force in an electric field. 2, it has to be moving so that it's not moving parallel to the magnetic field. If the magnetic field were to point to the right and I had a charged particle moving to the right, it would feel no force. It has to be moving at some angle. The force will be greatest when it's moving perpendicular to the magnetic field. So, moving charges experience a force in a magnetic field if they're moving at some angle to the field. If they're moving in the same direction as the magnetic field, they don't feel a force. And if they're not moving, they don't feel a force. Okay, what kind of force field surrounds a stationary electric charge? If the charge is not moving, it only has an electric field around it. If it's moving, it has both an electric field and a magnetic field. A charged particle has to be moving to produce a magnetic field, and it has to be moving to experience a magnetic force in an outside field. 4, and if there's any questions at any point, for those of you still with me, throw up a hand or do something in chat, and I will touch base at the end. 4, why will a magnet attract an ordinary nail or paper clip but not a wooden pencil? In order for a magnet to attract an object, that object has to have magnetic domains that can get lined up. So an ordinary nail or paper clip generally has iron in it. Iron can have magnetic domains that are lined up in different directions. If something doesn't have more domains pointing in one direction than another, it's not going to be magnetic. But if I bring a strong magnet nearby, I can cause the magnetic domains to align. Now, wood does not have magnetic domains that can get aligned. So the only way you can attract something with a magnet is if it has iron, nickel, and cobalt in it that can have magnetic domains that can align with the outside magnetic field. 5, why aren't permanent magnets really permanent? And the answer is, I can weaken a magnet by dropping it or heating it. Anytime I bang on the magnet or heat it up, it causes the domains to start to jostle, and they can jostle out of alignment. So if I drop a magnet enough times, eventually I will completely destroy its magnetism. 6, the north pole of a compass is attracted to the north pole of the Earth, yet like poles repel. Can you resolve this apparent dilemma? So let me just stop this for a second. The easiest way to just show this again is with the PowerPoint slides. So, is that down here? Magnetic north pole is the direction the north pole of a compass would point. Now, it's different than geographic north. They're not lined up. And like I said, the Earth's magnetic field has actually reversed like 20 times over the last 5 million years. So one, our compass is not pointing to true north, it's pointing to magnetic north. But the reason the north pole of a compass points in that direction is because magnetically, that is the south pole of the Earth's magnetic field. Opposite poles attract, so the north pole of a compass points to magnetic north because magnetically it's like the south pole of the Earth's magnetic field. Say that 10 times fast. If I were to ask this as a quiz question or something like that, well, you're not really drawing, but if I ask this for a live quiz, a lot of times people will just draw this kind of picture. The magnetic fields not lined up with the Earth's geographic poles, and it's changed direction many times over the last 5 million years. Okay, stop that share, going back to homework. 7, I answered already. 8, can an electron at rest be set into motion by the magnetic field? What if it were rest in an electric field? Remember, a charged particle has to be moving to feel a magnetic force in a magnetic field. And it has to be moving so that it's not moving parallel or in the opposite direction of the magnetic field. So if a charged particle is at rest, it doesn't feel a magnetic force, which means it can't be set into motion by the magnetic field. Now, a charged particle will always feel a force in an electric field. So if it were at rest in an electric field, it will feel a force, which means it will accelerate, which means it will start moving if it's at rest. So part A, can an electron at rest in a magnetic field be set into motion by the magnetic field? No, it has to be moving. What if it were at rest in an electric field? Yes, a charged particle at rest will feel a force in an electric field, so it can be set into motion. And last but not least, what changes in cosmic ray intensity at the Earth's surface would you expect during periods in which the Earth's magnetic field passed through a zero phase while undergoing pole reversals? Again, let me just stop this one and use this PowerPoint slide. Okay, so the Earth's magnetic field, unbelievably useful to us. It traps charged particles called cosmic rays that are all throughout space. These cosmic rays basically bounce back and forth between the poles. Every once in a while, they get enough energy somehow to escape the poles and stream into the Earth's magnetic field, or Earth's atmosphere. But if there was no magnetic field, there would be nothing to deflect these charged particles away or to trap them. And so all the charged particles, all the cosmic rays from space would enter the Earth's atmosphere and all sorts of havoc could ensue. And I mentioned earlier that what scientists think is a lot of evolution took place during these periods of time when the Earth's magnetic field was zero. All these cosmic rays came streaming through the Earth's atmosphere, caused mutations that then got passed along, and then a lot of evolution, in theory, happened during these periods. All right. So that's kind of it for going through the homework. So I'm going to hang out here for about 5 minutes. If you have any questions about anything Physics 10 related, let me know. If not, I appreciate everybody who tuned in, quote unquote, live and stayed around for office hours. So let me know if you have any questions. Close that. Can you go over number 6 again? A bit slower for me. Yes. Share screen. Oh, this is the one with north pole of a compass is attracted to the north pole of the Earth, yet like poles repel. Okay, so let me actually, I think I have another animation for this. Bar magnet, show the planet Earth. Okay, so one, let me just say that this animation is not 100% correct because the magnetic field and the geographic north, they're not lined up. So like this is showing that the magnetic field, oh, can I move this at all? No, I can move the Earth. Oh, fun. Anyway, so one, keep in mind here, the red is the north pole of the magnet. So if I move this compass, like here, it's pointing towards what we would call as magnetic north. That's the direction the north pole of a compass points. But opposite poles attract, which means if the north pole, let's say, is pointing straight up, that must be because it's attracted to the south pole of the Earth's magnetic field. So even though the north pole of a compass points towards magnetic north, it's pointing in that direction because magnetically, that is the south pole of the Earth's magnetic field. In essence, it's like there's a giant bar magnet buried inside the Earth. It's not really the case. It's because of some molten lava or something like that. And let me just stop this and show you the real, what it looks like. Go back up here. Okay, so this is a better picture of it. Let me, can I erase some of this stuff? Okay, so magnetic north pole, this is where your compass is going to point. The north geographic pole is sort of true north. So one, you have to be aware of the fact that your compass is not pointing to geographic north, it's pointing to magnetic north. But the reason it points to magnetic north is if I were to look at the Earth's magnetic field, it looks as if there's a giant bar magnet buried deep inside the Earth. And that bar magnet has its magnetic south in sort of the geographic north region. And again, this is just how the Earth's magnetic fields are right now. 500,000 years ago, it would have been completely different. Compasses would have pointed in a different direction. But right now, in our time, 2020, is that what it is? 2020, this is the way the Earth's magnetic field is lined up, is that here's true north, here's magnetic north, which means this is the direction the north pole of a compass would point. And the reason it points in that direction is because it looks like the Earth's magnetic field is created by a giant bar magnet where the south pole of the magnet is basically near geographic north. Did that answer, Allie? It's kind of a challenging concept, but keep in mind opposite poles attract. So if the north pole is going to point north, that's because it's attracted to a magnetic south pole. Did you already post the PowerPoint slides for chapter 23 and 24? That's a good question. Let me look. PowerPoint slides. Yes. So PowerPoint slides for the entire semester are already uploaded to your regular Physics 10 website. And just one more time for those of you, let me just remind you, I have also in your online resources page, oh, where is it? Oh, I'm now posting your quizzes and homework solutions. So I will post them, you know, after they are due, and I will try and start. I don't have that many people coming to sort of the office hours section. So what I'll probably start doing is just starting to answer some homework questions during office hours, just so that people can then go back and look at them if they need. All right, I am done for today. Well, done Physics 10. I got Physics 4A in a second. Thank you, everybody. And reminder, homework due on Thursday, quiz due on Friday. I got office hours tomorrow. I forget the time, but it's posted. And Thursday. And then Thursday, we are going to start chapter 19 on vibrations and waves. Very cool chapter. All right, did you already have a wonderful, wonderful, wonderful rest of the day? And I hope to see most of you on Thursday. All right, that's it.